Hello, today I, Jason Fox, and my partner, Nicholas Yu, will be discussing our project, The Finite Difference of Fins on CPUs. This project undergoes a finite element analysis in steady state and transient state on the fins with regards to a CPU that is outputting a constant temperature. The reason for this is we wish to see how finite element analysis could deal with more complex situations than those in class. To start with, we defined our boundary conditions as the left end will be at a temperature of 100 degrees C. This is because we are assuming the CPU to be the only source of heat and the CPU to also be constantly throttling at 100 degrees C. The fin will undergo no heat generation because it is a solid block of aluminum. And that aluminum has the constants K is 238 watts per meter Kelvin. With respect to air, we said that it was 20 watts per meter squared Kelvin. The outside temperature is 23 degrees C. And the length of the rod is 0.25 meters. The rod will undergo convective heat transfer. And so the other boundary condition is that at the end of the rod, there will be a conduction part and a convection part. And that will determine the boundary condition at the end of the rod. The rest of this page goes over how we found our finite element analysis equation, Tm, which is what is plugged into the computer to find the next node before reiterating. And then that is simplifies to this equation. And then I continued on and found the governing equation and the governing equation solution to compare with that finite element analysis solution. And the results for that can be seen here, where I used various end steps to demonstrate how larger and larger processing power can get you a more and more accurate result. As you can see, at end step is 10,000, we have a very accurate result that pretty much follows our analytical solution. And then I wanted to compare this solution with the solution if a fin was dominant. So I derived the fin equation for heat convection at the end. And that entire process can be seen here, and it ends with the equation at the bottom. Plugging that into MATLAB and finding what the temperature distribution is leads to this temperature distribution, which is remarkably similar to the one found through finite element analysis once again. This helps correlate that finite element analysis can be used to find the complex solutions to more complex geometries. And now for the transient solutions, I will hand off the explanation to my partner, Nicholas Yu.
So our transient formula is on the left, and basically it is the heat diffusion equation, but we also have to add in the heat loss from convection. With that, we have a PDE, which we plug into the PDE-PE function, and shown there are the coefficients that we would use. Then we have our initial condition at 296 Kelvin, and then our boundary conditions, which are 100 degrees Celsius or 373 Kelvin, and then KT is equal to dt over dx. Next slide. So these are the results from our code, and these are the same. This is the same result, but as you can see, the left side shows our base, which remains at a constant temperature, and on the right, it's more pronounced on the right corner, is the temperature slowly increasing with time, and also the temperature decreasing with distance. Next slide. So when we compared our results to a ANSYS solution, we found that our code was getting to steady state a lot faster than it should have been. On the right is the ANSYS at 3 seconds, which shows that the temperature has barely got through the fin, whereas on ours, we've already reached steady state at 3 seconds. Next slide. We also did it again at 100 degrees or 100 seconds, and this was just to have another viewpoint, but the results are still the same. The fin hasn't reached steady state, whereas ours has pretty much been steady state for the entire time. So even though our code seems to be incorrect. The outline looks very close to what it should be, so I think we are on the right track to complete or to make a more formal model for this.
Furthermore, since this technique can be used to solve partial differential equations of even complex fin problems, the entirety of the technique can be expanded upon to solve even more complex geometries. Thank you for listening. This has been our presentation. Have a good day, and I wish you a good rest of the semester.